So the shell sort is named after Dr. Shell. I think it was Doctor, but it's named after a person, and you're going to see pictures of shells inside of here because it's fun to play with that word. But this is a really clever, and you can see right here, slightly more complicated solution. So obviously, if you want things to be faster, then you typically have to come up with something a little bit more complicated. And this is definitely it. So the way this works is it actually breaks up the bigger list into sublists. And there's many ways that we can mathematically break it into sublists. One of the books I read breaks it down into factors of 2. Another one uses factors of 3. It doesn't really matter. Use whichever algorithm you come up with, whichever book you come up with. It's going to be better. There's still better ones yet for speed and efficiency. But while you have a sublist, basically what you do is, let's think of it this way. It's kind of the same as you take a deck of cards and split it into each of the 4 suits and then sort each of those in their turn. All right. So it kind of feels quicker because the cards are more familiar. Now, that's a human trick, but it actually works out in the computer system that if we have a list that is more closely sorted in the smaller bits, sorting the bigger bit, the whole list becomes faster as well. And this is the one that proves that. So what we do is we break it up into a bunch of sublists and organize those sublists, and then we blend the list together. But the thing that is that can easily be misconstrued inside of there is this algorithm actually doesn't take like the first half and the second half of the list and sort them, then merge them together. It actually creates a list mathematically that spans the whole larger list. So when we say the number of sublists, it's often referred to as H, and we'll see that in a second. What it's actually doing is it's going with, let's say, 10 sublists, and then it has 3 sublists, then it has 2 sublists, then it has 1 sublist, and then it's all sorted, right? It's one sublist being the list itself. So when we have 10, we basically look at every 10th number in the list. Not the first 10, but 0, and then 9, and then 19, and then 29, or however you want to break it up like that. And so we're starting with an index equal to the number of sublists. So again, we have 4 sublists. We start with number 4. And then we move up and then do 5 and 1. So we do 4 and 0, 5 and 1, 6 and 2, and so on and so forth till we get to the end of the list. And so as long as those 2 values inside of there that needs to be sorted, and we're not at the end of the list, we basically swap these 2 values higher and lower in the list. So since we have this big separation, we're taking the high values and moving them way to the end of the list, and the low values and way to the front of the list, much closer to the front of the list. And then we don't have to bubble them down as much. We're making big leaps inside of it. So think of it this way. If you're sorting a list of names, every time you see an A, B, C, you just toss that way to your left. And every time you see an X, Y, Z, you toss that way to your right. Doesn't have to be all the way where it's supposed to be, but I'm getting them much closer. And then when I come to sort the whole thing, then I'm dealing with everything that's fairly close. Again, fewer swaps that need to happen, fewer iterations that need to happen right there. And so we do that with one cut all the way through, and then we throw away some of the sublists. So we start maybe with 10, and then we drop down to 4 or 5, then we drop down to 2 or 3, then we get down to 1. So let's take a look at a very small instance of this example. Now this is tough because it is a small example, but it gets you the idea of it as well. So again, we have a value here, H. And it kind of acts, I says bubble sort here. You're supposed to say an insert sort. I don't know what I did. I should have fixed that. I apologize. So it kind of acts like an insert sort here, but we're doing it across a big sequence here. So you can see H is equal to 4, so I is set to be 4. And then J is also set to be 4. But we compare it to something that's 4 less, the number of H less here. So we start with 0, so 4 and 0. So we compare J with 0, I and S here. And they're different, so I gets moved all the way down the bottom and S gets moved halfway up the whole list. And then we keep moving up, O and N. Well, N is low too, so N gets kicked all the way to the bottom, and J and O gets kicked up to J, so pretty far up in the list. Keep going, R and G, well, look at this. Now we really do have some small values down at the bottom, and the bigger values end up at the top. F and Z, T, excuse me, still doing the same thing. U and N, well, this doesn't swap anything because U is greater than N. N and O, swap those two. So O kind of gets pushed off to the side, a little bit high, but we get the feel for this. We're seeing the small ones being thrown way to the left, the large ones being thrown way to the right. Now, because it's so small of a list, the next iteration here, H actually went down to 1 in the algorithm I was working on. Oops, sorry. So now it just basically acts just like an insert sort. It's going to be looking at one at a time, and it's going to be swapping them, in place, and it'll end up. It does the whole algorithm, but now note everything is much closer to where it started with. Just that one quick span moved everything much closer to where it started with. It cuts a ton of time off of the overall the solution for this, the overall runtime of all this. So, like the insertion sort, here's where I have the correct word. I apologize. It skips big portions of the list already. So if it gets to the point where things aren't skip, are pretty much in order, it'll just skip through and stop going from there. But it creates good chunks of the list that are sorted. They're ready to go. And it actually doesn't matter at all if the list is already sorted. It'll go through it very, very quickly at that point. So it is a really, really useful, highly efficient algorithm compared to the ones we've seen so far. Um, Later on, we'll come to some algorithms that are even more efficient, but this one is a really great bridge between complexity and understandability that really gets us something we can visualize and see what's going on. We kind of can get a feel for that. I mean, if you've ever sorted something, I definitely, when I sort things, I just kind of put them in piles that are close to each other, and then I sort each of those piles and then finish it up from there. And that, for me, intuitively has been a fast way to sort things for years. We'll see if it's intuitive for you as well, because now is your chance to go off and code the shell sort and see if you come up with a quick and fast working solution as well.